All right, so chapter 19 and 20 are about electricity, but a little bit more relatable than electric fields, right? We've been studying electric fields, electric forces, and it's very difficult to see them because they're not always tangible things. Even electricity flowing is not always tangible, but at least you can see like light. You see electricity being used. You charge your phone. You charge the battery really on the phone. If there's a power outage, you have a backup generator in your house. All these things involve electricity, clearly. There was a show, I think it might have gotten canceled actually, but there was a show where electricity stopped working. Anybody know what I'm talking about? I forget the name of it though. It's like that, but it's not. That's another show like that too, actually. That's a little different. There was a show out last year. I watched like the first season of it. It was kind of bad though. But the show, the premise of the show was imagine a world where suddenly electricity just stopped.
Was that the one with the dinosaurs?
No, that was another one that was actually pretty good too. I watched the beginning of that show.
Revolution?
Revolution, yeah, that's it. Revolution. So, listen guys, can we, is it warm or no?
Got 3.5 stars on it.
Is it warm in here or no? I feel like I have a fever tonight.
I'm sorry for this random. Did we ever get test feedback? It's not in Dropbox.
Maybe not. The picture of it's not in Dropbox? Oh. Okay, remind me, tomorrow we have a double, I'll bring them in so you can at least see them. Yeah, I think I let you see them real quick, but I may not have taken a picture. Maybe I graded it during school.
Yeah, you just told us the grading.
If you want to know, let me know. I'll definitely show you tomorrow. Are you watching the teaser for Revolution right now? It is a good show. I've seen it. No, I have. I think it's a great show. But out of 10?
No.
Oh, out of 5. I mean, shows are usually rated out of 10, I thought. Is it canceled though, or is it coming back?
I think it's
I think I got canceled, I'm pretty sure. Because it's been over a year now. Anyway, guys, let's get back to the point of the class. So the premise of the show was what happened if electricity stopped working. And what it really kind of led to was the idea that everything is based on electricity now. And that it really is true. Before we had discovered, right, we didn't invent electricity. Let's make sure we're clear about that. Electricity was never invented. Devices were invented to harness and use electricity, but electricity itself was discovered. And the easy way to think about electricity and being discovered is an abundance of charges. And that's where lightning really comes from. Lightning is an imbalance of electrons and clouds. Lightning can move from cloud to cloud or from cloud to the ground. So what we're going to look at in this chapter and the next chapter is all the theory that is involved with electrical flow. So circuitry, resistors, capacitors, batteries, voltage, current, all these terms that I'm throwing out there, all the things that would be involved with electricity. After that, we're going to spend, that's the first test. Then we're going to spend some time looking at modern physics, things that are like nuclear physics and atomic physics and stuff that is more modern day. Then in the third section of the quarter, the third test, we're going to look at fluid mechanics and heat transfer. Okay, so that's the rest of the quarter, so you have an idea for the year where we're at. So let's go back to 19.1 then. So in 19.1, we're going to take a look at some properties of current. We're going to talk about speed, the speed of the electrons versus the electric field. And then we're going to talk about direct and indirect, or direct and alternating currents. Okay, what the differences are. We'll also look at batteries and generators to understand how they work. This section is primarily theoretical. There's one small mathematical application, which you're seeing right here. And this is our definition to start. So, Jake, want to read for us?
Current, the rate at which electric charges move through a given area, i.e. machinery, appliances, computers, the human body.
All right, so let's pause and we'll go over what the idea behind current. So, the common misconception, okay, because most people recognize that when we look at current, when we look at like a light bulb generating light, we know that electrons are responsible, right? It's the electrons that are really responsible for carrying that electrical charge. The electrons are not moving at the speed of light. They are not moving at the speed of light. Okay, this is not a measurement of the flow of the speed of the current. It is the amount of electric charges moving through a given area. So let me give you a quick analogy. All right, simple analogy. How many people here are runners or run, or have run at some point in their life, or run in a race or something? Okay, I think everybody has run or done some sort of running. When you're running, when you're running, you can measure your speed, right? You take how long it took you, divide it into the mile, you know distance over time, you get your rate, blah, blah, blah. Easy. Now, you're not measuring the rate that the electrons are moving in a circuit. What you're measuring is simple. What you're measuring is this. Imagine, God bless you, that in a race, at the starting line, when you start a marathon or a half marathon, they go in heats. So a group of people go. They wait 20 minutes. Another group of people go. They wait 20 minutes. And they mark down when you started, and they mark down when you end, so that everybody's not running over each other. So it's not a stampede. Now, in the beginning of the race, everybody's lined up at the starting line. And the people that are in that heat, that might have a lower time, might be behind them. But usually everybody comes toward the starting line. So a lot of people cross the starting line at the same time. Right? In the very beginning of the race. A ton of people cross the starting line at the exact same time. But at the checkpoints throughout the race, people are spread out a little more, aren't they?
Yeah.
When everybody is gathered in the beginning of the race at the starting line, and they all pass that location, the starting line, at the same time, that's the equivalent of it being like a higher current. Think of the people as electrons. A lot of electrons passing a given location at the same time is a high current. If the electrons are spread out, and only like 2 electrons pass, and then 3 electrons pass, and then you wait a little more, and then 5 electrons pass, that'd be a lower current. So it's the rate, or like the density of electrons crossing a given area at a given, or in a given time. So we're going to see our formula in a minute relates this, but so you understand the theory behind it, it is not the actual speed of the electrons. You're not measuring speed here. Okay, it's a flow, so you want to think of it as like a flow rate. So like if you think about like when you fill up your gas tank, it's in gallons per minute, the amount of flow rate. And then the amount of fluid that comes in your gas tank is in gallons. When you run, your measurement is in miles per hour. The distance you run is measured in miles. This is not like that. Is that clear? Okay, but we're going to make analogies to flow rate in a pipe because electric flow rate does behave similarly to that. Okay, but the actual measurement is not the same at all. So let's look at our actual equation here. We see delta Q over delta T. Now, I stands for current. What did Q stand for? That's something you should know from the last chapter. What was Q? If you don't remember, maybe you know the units at least. Not energy, but close. Close. Energy would be joules, right? And you want to think it's like energy because we did some measurements last chapter. We talked about having a lower or a higher Q value. If the 2 particles had very high Q values, the Fe was very large. Remember Q was in the formulas? Q1, Q2, it was a lowercase q. What did Q measure? The what? What's the word for it? The charge. Good. Remember Q was measured in coulombs. And it was like a point charge, or a source charge, or a test charge. But it was always measuring the charge. So, delta Q is the amount of charge, whatever you're doing, stop, is the amount of charge passing, okay, that given location. So it's measured in coulombs, because it's Q. Delta T is what? Time, okay, change in time. So our units here are coulombs per second, really. We have a coulomb in the numerator, seconds in the denominator, and a coulomb per second is defined as an amp. So you've heard this term before probably. If you know anything about electricity, the term amps or amp. Amp. Some people say ampage. It's not a word. It doesn't exist. The word is current. Okay. The actual real word is amperes. Okay. How many amperes? An ampere is a coulomb per second, known as amps. You sometimes hear even electricians say, "What's the ampage on it?" Ampage is not actually a word. Okay. I mean, maybe it's been accepted like in like slang dictionaries or as a colloquium, but it's the current. What is the flow rate? Okay, the current. So we're looking here, in this case again, I is the current, Q is the amount of charge passing a given location in a given time period. Okay, in a given time period. Whenever you hear anything divided by time, you know it's a rate. Velocity is really a rate. God bless you. Volume of fluid flowing in a pipe is a volumetric flow rate. What else? I don't know. There's a lot of things that are rates, but anything over time is a rate. So keep that in the back of your mind. This is a measurement of a rate here. So let's talk about the actual flow. So first, we know, and we talk about electrons flowing a lot. We talk about electrons carrying charge. That it's really the electrons that are moving in the circuit, but positive charges can also travel. Okay, which is very misleading because you assume the positive charges, well, they're in the nucleus. Things in the nucleus can't come out of the nucleus, so how could the positive charges be moving, right? But positive charges can move. A simple example would be like a particle accelerator. Another example would be, remember last year in chemistry for extra credit, I think you guys did this? I remember somebody telling me there was like you made like a salt bridge, like a battery in essence, and you had to measure the voltage, right?
Yeah.
Did you use pennies for this and stuff, or is it the one? Okay. So in that example, whenever you have a salt bridge or some sort of ions in a fluid, the positive charges and the negative charges are both moving. Okay, so whether it's negative charges or positive charges moving, it doesn't matter. What I want you to know though is that physicists a while back, this was hundreds of years ago, accepted current to be defined as the flow of positive charge, which is a bit misleading because you think of electrons moving. Okay, so for example, these are the electrons. See them? They're moving to the left. Take a pipe. Think about a pipe. Slim it down. It becomes a wire, doesn't it?
Mm-hmm.
Think about a pipe in your mind, or a metal rod. I think there's a metal rod over here. Yeah, there is. Slim it down a lot. Okay, think about this metal rod. It's like solid metal. This is really just a wire, but a thick wire. That's all it is. Okay? So when we're looking at this, if you look at the diagram on the board, if you take a cut through this rod or through this gigantic, exaggerated wire, take a slice of it, that cross-sectional area is a circle. You see that? If I slice through here, I would get a circle on the end of it. If I slice at an angle, I get like an ellipse actually. But let's use a perpendicular slice. So it's a circle. So what we're doing here again is we're measuring the amount of charges passing this location. Okay, that's what the current is. And now the current again is the measurement that positive charges would flow. It's the opposite of negative charge. It's just an adoption that physicists took a long time ago, and every book you're going to read is going to say this, so I'm not going to teach it the other way, but you should understand that when we talk about charge carriers moving, it's really the electrons that are flowing through the circuit. Okay, but current is measured in the direction that positive charge would flow. The direction that positive charge would flow. All right, let's take a look. I think I want to jump to an example. Yeah, let's jump right to an example now. Ed, why don't you read this for us? Go for it.
This startup current for standard refrigerator around 15 amps, but the running current is around 3 amps. For a 10-second time interval, how much more charge passes a given point in the circuit during the startup mode than the running mode?
All right, so before we attack this problem, let's talk. Because we haven't done anything with thermodynamics or heat transfer yet. So this might not be clear as to why this is. Why would you think that when you start a refrigerator up, it uses more energy than when it's running for days? Why is the rate of energy used more at the beginning than at the end?
Because it has like build up temperature maybe, and then after it stays constant, right? Oh.
Yeah, keep going.
Okay. So it's like build up the temperature, and then once it reaches that, it just kind of stays there.
That's exactly right. So in the beginning, it needs to reach like an equilibrium temperature, we'd say. The setting we turn it to. Once it reaches that setting, it's just maintaining that now, right? What is that analogous to? Somebody in the other class got it. Yeah, very good, Paul. Julia Montana said it right away in the pictures. That's like friction. It's exactly right. Static friction and kinetic friction. To get something moving, it takes more force, right? But once it's moving, it takes less. So again, the beauty of physics are two completely different things are actually similar. So in this example, we're seeing that it takes more current to get a refrigerator going than it does to keep it going. That's what we're noticing. Okay? Now, other stuff we're going to talk about with refrigeration we'll talk about later, but there's a lot of interesting stuff with refrigeration. Believe it or not, another misconception would be this. The more stuff you put in the fridge, the less energy it uses. You would think, right? If I take a ton of stuff that's really warm, put it in the fridge, it would take a lot of energy to cool it down. And it does initially. But in the long run, the less volume of air that's in the fridge, the more it's packed, the easier it is to keep it at a cold temperature. It's like, think about a freezer. If you have an ice chest, like an old school ice chest where you actually lift the freezer up, usually it's pretty much like filled to the top. Everything in there is frozen. So it doesn't take much to keep it cold, because it's like ice acting within ice. The inside that's frozen is keeping everything else cold, so this thing doesn't take much. A refrigerator works by doing what? Anyone know how it actually works? It's the same way an air conditioner will work, if you know how an air conditioner works.
I think there's like Freon or something.
Freon?
Yeah, that runs through pipes, and then I guess the cold is radiated out through the wall or something. It's like because the actual refrigerator it's basically an insulator, but the pipes are like frozen or whatever.
Yeah, you're on the right track. There's Freon moving through it. The fridge itself acts as an insulator, very good, keeping the cold in. The thing that most people don't know without either reading about it or learning about this is that a refrigerator doesn't actually add cold, it removes heat. And we haven't done heat transfer yet. We're going to do that within a year. So had I mentioned that already, it would make more sense, right? Heat only moves from hot to cold. Only. It's never a heat transfer the other direction. It doesn't exist. It can't happen. So a refrigerator works by removing hot air. That's why when you stand in front of a refrigerator, you feel your feet get kind of warm, or you feel like the tile in front of a refrigerator is pretty warm usually. It's because it's removing the hot air that's in there. Now, it's not just hot air, though. So inside of, say you put, I don't know, a 2-liter bottle of soda or a gallon of water in the fridge that's room temperature. It's removing the heat from the water, which in essence is chilling or cooling the water off. And that heat has to go somewhere. So the Freon, or what's called a refrigerant, Freon is called like our 134A or something else, code names. A refrigerant goes through the fridge, through those coils in the fridge, absorbs the heat that it's getting rid of. Okay, it also, there is cold air coming in. You are going to see a fan and stuff. But it absorbs that heat, even like an air conditioner. And then it goes through a cycle which cools the refrigerant again and then absorbs more heat. And it absorbs more heat. But to cool the refrigerant down, that's what you're using electricity for. That's the reason. I mean, the fan also. The fan is minimal compared to that.
Is there such thing as a portable air conditioner? I was talking about this with my dad when we were like.
There is, but what has to happen is you have to have a ventilation shaft. So the ones they make now, it's an air conditioner that's they're used in construction sites in the summertime. Think about a construction site that hasn't been finished yet, right? It can be hot as anything outside. So what they do is it's a portable air conditioner and it runs a hose outside. And all the hot air that it's removing from the room goes to that pipe. You need some sort of HVAC system, HVAC. So, I mean, it could be in the window. Some of the ones are, if you don't have, like, if you can't install one in your window at home. Anybody ever have windows that slide open like a balcony door would? A lot of those, you can't install an air conditioner, right? So you have the portable ones, and they have these like vertical shafts at the end, and a pipe comes, feeds into the, a good analogy. Ever seen like a vacuum cleaner and the attachment when you want to like clean the steps? It looks like a rectangular head, and then the pipe comes out of it. Imagine that, but blow it up much bigger. Imagine a vertical rectangular head coming out of a hose. It would look like this. Okay, and this is from the side view. Here's the vacuum cleaner over here, and then all the air would travel through here, and then it would go out the window if you slid the window left or right. So yeah, they do exist, but they're not usually used in consumer or I guess home appliances because they're not energy efficient. These ones are much more energy efficient because they're installed with proper insulation. Because the minute you have a pipe going out or something like this, there's air gaps in the window. When you open the door, there's a little air gap there. These are all like supposed to be like perfectly insulated. This is an old building, so you guys all know they're not, right? Like these windows are clearly not insulated properly. And you can feel it in the wintertime a lot of the time. But again, it has to do with the age of the building. All right, let's keep track of this. So now we want to figure out what the difference is in the amount of charge used in a 10-second interval. Okay, the amount of difference in the charge. So this is a very simple example mathematically I just wanted to give you because there's not much more we're going to do with this formula. This formula is not very useful. Okay, usually you measure current with an actual what's called a voltmeter or a multimeter. A multimeter measures resistance, voltage, current. It measures it all for you. Usually you don't calculate current, but I want you to see how it's a very simple thing to do. All right, so we've got first, at startup mode, the current is 15 amps. Once it's been running for a while, the current is 3 amps. So I'm going to call that I1 and I2, just because they're two different scenarios. I know that in a 10-second interval is what we're looking for here. So even in startup mode, I'm trying to figure out in a 10-second interval, and also when it's been running for a while, how much charge is used in a 10-second interval. Now obviously, the more charge used, the more energy used, the more money you pay. So when you turn a refrigerator on in the beginning, that's where a lot of the energy consumption is coming from. That's why you don't turn a refrigerator off and on. I mean, besides the fact that you spoil your food, but a refrigerator does not cycle between temperatures ever. It maintains the temperature. It reaches what Victoria mentioned earlier, known as like the equilibrium temperature. So as a result here, we can calculate the charge that would be crossed across the circuit in a given time period. So let's go ahead and do that. Let's use our formula here. What am I solving for? What variable? Good. Why am I solving for Q? Who said that? Kira? Good. Q is the charge. We're looking for the amount of charge in these two scenarios. So solve this algebraically for Q. We get I times delta T equals delta Q. Okay, that's the formula we're going to use for this. But how many times do we have to use this formula? Twice. Okay? Scenario 1 and scenario 2. The other option is to look at your change in current. What's the change in current? 15 minus 3? So you can technically use 12 here, multiplied by a 10-second time period, and you'll get the change in or the difference in the charge between the two scenarios. But let's calculate it twice just for the sake of it. So in scenario 1, 15 amps over a period of 10 seconds gives me 150 coulombs of charge. That's in scenario 1. How do I know it's coulombs besides the fact that, charge is measured in coulombs? How do I know it's coulombs from this equation? What does an amp stand for again? What's an amp? You both hands popped up. Yeah, coulombs per second. So coulombs per second times second gives you just coulombs. Okay? And in the second scenario, it's the same thing, just change what number? Okay, change it to 3, please. Very good. And we get 30. So the question in this problem is specific, and I want to make sure we answer the correct question. The question stated, how much more charge passes a given point in the circuit? How much more? So what's the answer? What's the answer? 120 units? Coulombs, right? Agreed. Now, how could this problem be changed so that the answer was 5? Think about it for a second. If I gave you an answer of 5 as a multiple choice for this, what would the problem have to be asking for you to come up with 5 as the answer? No units, just the number 5. How many more times larger? Or by what factor of increase? Or by what factor? Or how many more times? You see the difference there? Anyone that's interested in the SAT subject test in physics, you got to know the difference here. Because these are things that you're going to be asked. How much more? How many more times? Okay, in this case, it was how much more. So the answer would be 150 minus 30, which is 120 coulombs. Okay? Different from how many more times. Next thing we're going to look at is this concept of drift velocity. Now, drift velocity is the idea that we talked about earlier, that electrons are not flowing at the speed of light. They're not even flowing anywhere near the speed of light. They're far lower than the speed of light. So what's happening? The electrons exit the battery with a certain amount of charge. We call them charge carriers. Okay, charge carrier, in this case electron. They exit the battery, they go through the circuit, they reach the resistor or the light or whatever the element is. That energy is used up. They have no energy left, they go back to the battery, and then they recharge, and they go through the circuit again. That's physically what's happening. While the electrons are moving through the circuit, they're bumping into things. They're bumping into the metallic atoms in the copper wire, or in the gold-plated wire, whatever material it is. So what kind of motion do they have? This is the kind of motion they have. It's not straight line motion. It's a lot of it's randomness, actually. As they collide with other atoms, I should say, not molecules, but atoms, they start to bounce back and forth. So this is the path an electron or a charge carrier would take. So it's not moving at the speed of light. But for some reason, when I turn this on, is there any delay? I mean, that's a bad example because these lights actually have a little delay. And when you turn the light switch on, usually there's no delay in the light. It turns right on right away. Or you turn on something that's electrical, you see the light shine right away. You click a flashlight on, the bulb lights right away. Well, it wouldn't make sense because the electron's moving so slow. So here's what's happening. There's a theoretical idea for you. When you turn on a light switch, which is in essence what's called closing the circuit, when you close the circuit, when you turn on the light switch, what happens is an electric field is established. The minute there's a connection and there's a battery, there's a positive end and a negative end. There's a positive and negative terminal. Between them, there's some electric field. That's what we're looking at, capital E, electric field. That electric field moves at the speed of light. And it communicates to the charge carriers to start moving. Move a little bit at a time. Not fast, but just move. But because the electric field travels at the speed of light, the light turns on instantaneously. We don't have any real delay in the light, or the circuit, or whatever it may be. Because the electric field tells everything to start moving right away. But the electrons themselves are moving literally. I'll give you the number. You're not going to believe how small this is. Okay, the speed of light, if you recall, 3 times 10 to the 8th meters per second, or 186,000 miles per second, believe it or not. It's a crazy speed. But the speed of electrons in a circuit is 2.5 times 10 to the negative 4, which is really like a quarter of a millimeter every second. Think about a millimeter. Millimeter is that small increment. Small increment on a ruler, right? Really small. Here's a quarter of a millimeter every second. I mean, literally, what I'm doing right now. Do you even see me moving much? That's the speed that electrons are moving at. They're just moving real slow. Okay, and tomorrow I'm going to show you a quick, simple way to think about it. Okay? We're going to run out of time today to do it though. But the idea is that the electrons themselves are moving very, very, very slow. They might move in one direction, they might go back and forth. We'll talk about that in a moment. Okay, but that's what drift velocity is. The actual velocity of the electrons being very, very slow.
If they move that slow, isn't the spacing of the move between them pretty short? Or not usually?
They're going to move through the entire circuit, actually. They will go through the whole circuit if it's direct current. If it's alternating, all they do is move, and move back, and move, and they're just actually oscillating back and forth. Now, relative to the size of an electron, this is actually a pretty good speed. It's very small, right? A quarter of a millimeter every second. But the fact that an electron's size is on the atomic level, and we're looking at like a radius where we're at like nanometers, it's actually a pretty decent sized velocity for an electron. Right? It'd be like comparing a human's velocity to that of a... Imagine if there were really, like, remember Transformers, the movie? Imagine if Transformers were a real thing, and they were like running. Every one of the Transformer steps would be huge gaps, wouldn't it? So their speed would be much bigger than a human, although it might look, relatively speaking, you might say, well, that's pretty fast for a Transformer. It's not a slow speed for an electron, but relatively speaking, it's a slow speed. Okay? Two types of current that are given, two sources of current. First, batteries, and you did this in chemistry, as the bonus you guys did. What's happening here is you have ions, and the ions want to move away from the negative end, or the anode. This is the negative terminal. So negative ions are moving, these electrons are flowing through the light bulb, they're getting used up by the light bulb, they're coming back in over here, they're getting recharged and then flowing back out. A battery has to convert chemical to electrical energy, always. A chemical to electrical. The batteries that you guys use every day, you're not plugged in, the batteries that you guys use every day on your cell phones, those lithium batteries, are rechargeable. It's not the same thing that you're seeing here with like some sort of battery acid. But what's inside those batteries is a lot more complex than what you're seeing. Now, the generator is the kind of not the opposite, but kind of the other end of the spectrum. Take mechanical energy and convert it to electrical. So think about it at home. When the power goes out, if you live in the suburbs, those probably know, you have a generator that might turn the house back on. Or you go to the basement and you turn a crank, or you pull on what looks like a lawnmower engine, and you start to pull on the generator, and then since there's gas in the generator, it's acting like a battery at that point. But you need to generate some starting energy by rotating a magnet and getting it started first. So that's why that's the same way a lawnmower will work. When you pull on a lawnmower, you're putting in mechanical energy. It's a generator first. But then once gas starts being used, it acts like a battery. It's using up some sort of chemical resource. The idea behind this I'm going to show you tomorrow. Yeah, maybe at the end of this class. Okay, so generator is mechanical to electrical. An easy example of a generator is like a windmill. Right? A windmill takes mechanical energy, rotational, and turns it into electrical energy. The way it works is with a magnetic field, and we'll talk about how that works with like a solenoid and electromagnet soon. Now, there are two types of current. Current can flow through a wire in one direction only, and that's known as direct current. When we do the lab in this, we're going to hook up a little circuit board and see how it goes with light bulbs, power the bulbs, with different dimnesses and brightnesses. We're going to have resistors and capacitor in one location. We can change the capacitor to alter the brightness of the bulb. It's pretty interesting, I think. That's all direct current. It's flowing out the battery, through the circuit, back into the battery. Charges, out the battery, back in, and so forth. In alternating current, what happens is this. The terminals, the positive and negative, are constantly changing. So the electrons do that thing that Kira was kind of asking about. The electrons just move back and forth. That's all they're doing. They're kind of like vibrating and shifting back and forth. So for an alternating current, what's happening is they move this way in the circuit, then they move this way. Then they move this way, then they move this way. But it happens so fast that you don't notice it. In the US, we use alternating current. Why isn't this light flickering? Why isn't it turning on and off? It is. Right now, that bulb that's coming out of here, this light that I'm turning on right now, it's flickering right now. But you don't see it flickering because it's flickering at 120 hertz. 120 times every second it flickers. Your eyes can't pick up on it. Ever look at the back tire of a car? When it spins fast enough, it almost looks like it's going backwards because your eyes can't pick up on the speed, so the losing is behind it. Same exact idea there. Okay, tonight there is homework in this, please. Okay, do the homework in this section, please. Look at these examples tomorrow. A double tomorrow.